Measurements are extremely important in science, and the way we measure the amount of a substance or chemical is with a very specific measurement value called a mole. A mole is a unit of measurement that is defined by Avogadro's number. The number is 6.02 times 10 to the 23rd. You can think of this value as a constant that is used to count the number of something, in the same way that you would use 12 as a number to count a value of 1 dozen. So if you had 1 dozen eggs, it would mean you have 12 eggs. And if you have 1 mole of eggs, it would mean you have 6.02 times 10 to the 23rd eggs. And that's a lot of eggs. As you can see with the largely positive exponent of 23, this value is very, very large. A mole is a large number by design, as it needs to efficiently count substances that we call elementary entities, which are atoms, molecules, ions, electrons, or any other very small group of particles. So, Avogadro's number is a defined value of 6.02 times 10 to the 23rd particles, which is 602 sextillion particles, which again equals 1 mole. Because Avogadro's number relates the two units of measurement, which are particles and moles, we can use this value as a conversion factor between the two. In this case, we would take the number of particles, 6.02 times 10 to the 23rd, and place it over 1 mole, which can be used as a conversion because dividing this out equals 1. So let's say you had a glass of water that contained 13.3 moles of water. How many actual water molecules would you find in that glass of water? Let's use our conversion factor. We start with 13.3 moles of water and then multiply by our conversion factor, which we know that 1 mole of a substance equals 6.02 times 10 to the 23rd molecules. We multiply across. 13.3 times 6.02 times 10 to the 23rd equals about 8.0066 times 10 to the 24th for the numerator. The denominator is 1, and the mole units cancel out. So we can say that 13.3 moles of water has around 8 septillion, move the decimal 24 places to the right, molecules within it. As that is such a large number, you can see how it is easier to just measure and talk about it in terms of moles. This conversion factor will be used throughout your entire IB chemistry course, so be sure to remember it and get used to using it. Now that we have discussed how we can use the mole and the amount of particles as units of measurement in chemistry, we will discuss how we also use mass to quantify various chemicals. How can we find the mass of a particular atom or molecule? Luckily, this information about relative atomic mass has been laid out for us by previous scientists on the periodic table. Typically, a periodic table will have two numbers that accompany each element, the smaller number being the atomic number and larger number being the relative atomic mass, which means the mass of a singular atom. The reason why it is called relative atomic mass is because these masses you see on the periodic table are all relative to the mass of 1/12 a carbon atom's mass. So if you take a look at the periodic table here, you will notice that oxygen has a relative atomic mass of about 16 units, which is saying an oxygen atom is 16 times the mass of 1/12 a carbon atom. Something else to note is that relative atomic mass does not have any units because these values are generated from a ratio or comparison to carbon-12. So the units used for the masses end up canceling out. So what about relative formula mass? This is the exact same concept as the relative atomic mass, except it is for a compound or molecule with a more complex formula than a singular atom. Take this carbon dioxide molecule, for example. There is 1 carbon atom and 2 oxygen atoms. While we do not have CO2 on the periodic table, we can use the individual relative atomic masses of carbon and oxygen to calculate the overall relative formula mass of CO2. We will be adding up each relative atomic mass included in this compound. This includes the 12.01 units for carbon, the 16 units for oxygen, and another 16 units for the second oxygen. Be sure to pay close attention to the subscripts in the chemical formula to let you know how many of each element we must include in this calculation. In this case, since there are 2 oxygens, we can just multiply our 16 units by 2. Doing this will make your calculation easier, especially when you have larger subscripts and more complex molecules at hand. The relative formula mass of CO2 should come out to be 44.01 units. Determining the mass of a molecule is routine in chemistry, so the moment you notice you need a mass for a calculation, you should automatically refer to your periodic table for help. We just started using some values on the periodic table for the relative atomic masses, and we are doing so again for the molar masses. We can do this because the difference between relative atomic mass values and molar mass values is negligible. Now, what exactly is molar mass? Molar mass is the amount of mass that is present per 1 mole of a specific element, which is expressed in units of grams per mole. We can use these molar mass values shown by the periodic table as conversion factors to convert between mass and moles of a substance. For example, if you are carrying out a lab that requires you to measure out 0.5 moles of NaCl, you likely don't have a measuring device that has units of moles. But we do have electronic balances that measure in grams, which is the unit for mass. So we can find out how many grams we need to measure of NaCl by using the given value of 0.5 moles to begin with and multiplying this by the molar mass of NaCl. The molar mass can be found by checking the mass values for both sodium and chlorine on the periodic table. If we had 1 mole of sodium atoms, it would have a mass of about 22.99 grams. And if we had 1 mole of chlorine atoms, it would have a mass of about 35.45 grams. Adding these two values together, we get a molar mass for NaCl, which equals about 58.44 grams per mole. As you can see here, we must multiply our starting value by the molar mass because this is how we can get moles to cancel and leave us in units of grams. After multiplying these two values, we determine that we need to measure out 29.22 grams of NaCl for our lab, which is equal to 0.5 moles. In a hypothetical problem where we were given a known value in units of grams instead and needed to convert said value to moles, we would need to divide our starting value by the molar mass. If you are ever unsure of whether to multiply or divide, just remember to show the units in your work to ensure they will leave you with your desired unit after calculations. Like Avogadro's number, molar mass is another conversion factor you should get comfortable with using. These two conversion factors also have the mole in common, as Avogadro's number takes us from particles to moles and molar mass from moles to grams. If you ever find that you need to convert from particles to mass or vice versa, you will have to use both conversion factors in your calculation. Let's practice that with another example. Let's say a reaction we want to carry out requires 10.0 grams of potassium bromide, and we are curious of exactly how many particles of KBr we will be adding for this reaction. Before we start plugging numbers in for our calculation, let's map out exactly what we need to do for this two-step conversion. There is no conversion factor that bridges mass of a substance to the number of particles of that same substance. Since both mass and particles can be converted to moles, we will use this as our bridge. So, our first step will be converting from the given mass of KBr to moles of KBr. Our second step will be converting from the moles of KBr to particles of KBr. Now that we know the structure of our calculation, let's plug the numbers in. Our given amount of KBr is 10.0 grams. The conversion factor for grams to moles is molar mass. The molar mass for potassium is 39.098 grams per mole, and the molar mass for bromine is 79.904 grams per mole. Adding those together, we get 119.002 grams per mole as the molar mass for KBr, which we will place right here for our calculation. Notice that we desire to cancel grams out in this step to convert to moles of KBr. Because of this, we will divide by 119.002 grams, which leaves the 1 mole in the numerator and mole as the unit for our answer for this step. You can either do this step separately or calculate steps 1 and 2 together. Let's first go through the calculation with the two steps separately before seeing what it would look like combined. 10.0 grams of KBr divided by 119.002 grams of KBr and multiplied by 1 mole of KBr is equal to 0.0840 moles of KBr. Since our second step is converting from moles to particles, we will use the 0.0840 moles of KBr as our next starting value. The conversion factor for moles to particles is, that's right, Avogadro's number. 6.02 times 10 to the 23rd particles per mole. This time, our conversion factor has the unit we desire in the numerator of the unit, particles over 1 mole. So we will be multiplying our given value of 0.0840 moles of KBr by the 6.02 times 10 to the 23rd particles. This way, the 1 mole is on the bottom, canceling the unit of moles out and leaving us with an answer that has units of particles. So, 0.0840 moles of KBr multiplied by 6.02 times 10 to the 23rd particles of KBr and divided by 1 mole of KBr is equal to about 5.06 times 10 to the 22nd particles of KBr. It makes sense that our answer is smaller than Avogadro's number, the amount of particles in 1 mole, because 0.0840 moles is less than 1 mole. If we were to have calculated these two steps together, we would have written it like this. Notice that all the values and units are in the same places. An easy way to calculate a multi-step conversion like this is to A, multiply all the values at the top to find the numerator. 10.0 grams times 1 mole times 6.02 times 10 to the 23rd particles equals 6.02 times 10 to the 24th grams moles particles. This is a pretty funky unit right now, but that's because we haven't canceled anything out yet. B, multiply all the values at the bottom to find the denominator. 119.002 grams times 1 mole equals 119.002 grams moles. Lastly, C, divide the resulting numerator by the resulting denominator. 6.02 times 10 to the 24th divided by 119.002 equals 5.06 times 10 to the 22nd particles. You can see how the grams and moles canceled in this step and left us with the value we calculated using the separated method. Either way will get you the same answer as long as it is calculated correctly, but combining the steps may save you some time.